So let's take a look at some important application using autoencoder. Okay, for example, it's right here is denoising, right? We have an example right here, which is convolution autoencoder for image denoising. So the code is right here, so you can copy the code. However, I would like to explain what is the basic concept behind such kind of design. So basically, we know the idea of autoencoder looks like this, right? We have, for example, K. So basically, you can view autoencoder like this. Okay, a very simple structure. However, you can design your own autoencoder with a very complex structures with different layers with different neurons. Like okay, the basic is like this. So we require K should be less than N, and usually should be much smaller than N. So that okay, and I said, if the K is too small, you will lose a lot of information from the original X, right? But sometimes we set a smaller K deliberately. 中文讲 K 太小的话，我们会丢掉太多的。可是有的时候啊，我们是刻意的、人工的，这 deliberate 把 K 设的稍微小一点，比你平常的认知再小一点。Why we do so? Usually when we say, okay, the axis looks like this. There's a 784 dimension pixel, right? So it's one of the example that appearing at X2. However, sometimes the data we collect from the real world, they have a lot of noise. As you can see, the figure looks a little bit fuzzy, right? Right. So before we do classification, no matter the classifier you use is a convolution neural network, is a dense neural network, whatever, you have to clean the data, right? As we mentioned before, some unsupervised learning algorithms like principal component, like autoencoder, right? They shrink their dimension, so they lose a lot of information if the dimension is too small. But however, we can see that there are a lot of noise in original data, right? So if it is possible for us to design a neural network before we analyze the data, can we clean, or we say, can we denoise those noise before we do neural network classifier afterward? So basically, if the PCA or the autoencoder, they deliberately set the K value to smaller than usual, they might be able to remove unimportant data from the original data set. 我再讲一次哈，我们如果刻意的设计一些unsupervised learning 的东西，像 PCA 或者 A， 我们让它的那个 K 的值比平常要来的稍微小一点点。那我们知道那个 K 值变小，我们前面讲过嘛 ，K 值变小 ，K dimension 变小的时候，它会丢掉一些 information 从原本的那个 space 里面丢掉一些 information。而如果很恰巧的丢掉的那一些 information 正好是我们不想要的，有没有可能？当然是有可能。所以以下面这个例子来说啊，下面那个手写数字的2看起来是很清晰的嘛，上面那个是有点 fuzzy， 就是有点模糊，因为它有很多杂讯点在里面。如果我们可以刻意的让 K 设的小一点点，然后让它 denoise 一样我们就做一个 autoencoder， 好，我们做一个那个 PCA 都可以 ，K 比平常设小一点的话，因为 autoencoder 或者是 PCA 是要保留最大的 variance， 对不对 ？autoencoder 是要还原嘛，对不对？可是如果在还原的过程中，或者在保留 variance 的过程中，它刚好拿掉的 K+1、K+2、K+3， 或者一直到 dn 的维度，刚好都是形容那些 noise 的，那么我就可以很轻的用这些 PCA autoencoder 这样子的把那些 noise 拿掉。希望你都理解。那你一定会想说，那为什么我拿掉的是 noise， 而不是比如说很清晰的那个2、1、0的那些那个里面的手指数字？为什么拿掉的刚刚好就是 noise？应该说这件事情就是这样，就是说，如果 noise 是很均匀的散布在原本的资料里面的话，它就比较不重要，对吧？我们口语是这样讲。那比较不重要，在数学的意思是什么？就是 variance 比较排比较后面的，或是 entropy 比较大、比较散的。所以自然而然的话，那个设计应该是对的，就是我们用 autoencoder 或是 PCA， 那个 variance 比较杂、比较小的那些波动就会在排比较后面。如果你用一般的波来显示的话，就是说，or we take another example right here. Okay, we use a wave to describe what is noise and how to denoise. Okay, for example, that is the original data. Okay, and I have a wave such a wave like this. So maybe you can see that is time, right? And that is the packet. the number of packets I receive from my network. I would like to analyze those packets. So what is noise? Basically, noise is some unimportant or irrelative packet. So basically, we will increase some noises like this. They will follow the original trend. But however, there are some noises. They will increase the amount of packet you receive from your routers. Okay, sometimes noise is higher, bigger. So basically, you have an original trend and you have a noise. So if you analyze such kind of things, I recommend you use a denoise, for example, PC or autoencoder to represent the original data. So you can remove all those green parts. It takes some time to think about it. Okay, that is one of the way to apply autoencoder to do that denoising. The other things is very similar to denoising. It's called anomaly detection. And of course, you can find the code, the denoising code by right here. Okay, Kira says a corresponding code, so you can just follow the code and teach you how to write the denoising code by using autoencoder. Okay, the other one is anomaly detection. That is relative to our topic, right? To identify if there's any anomaly from your network traffic trace, from you want to know if there's anything wrong with your system, is there anything wrong with your network, something like that. We want to do detection. Okay, how do we do so? Here again, we have some data right here, and we don't have Y, right? Because this is unsupervised learning. Okay, so among those training data, we design an autoencoder to transform those training data from n dimension to k dimension. So that is the data space we want to use. The weights right here and the weights right here. Weights are trained by training data and right here. So the weights right here, W or W prime, they are highly related to the data you provided, right? Because you have n data points. So you have n data points to train these weights. So they can learn how to map those data from high dimension to low dimension and then recover them from low dimension. So that's a kind of mapping. So you can draw it in this way, okay? So here we have a original space, and I use green color to represent the new space, okay? And we have a new learning space. Originally, the data they might have some kind of distribution 就是说在原空间里面假如那个 x 值是表示一些很简单的东西，比如说你的身高跟体重好了，那我们有 n 个人嘛，对不对？所以这 x 里面可能就有每个人的身高跟体重关系。Okay, so maybe that is x1 to x2 and so on and so forth. Okay, we have micro dimension. Okay, so there is a data point right here, p1. There's data point right here, p2. After we do such kind of space mapping, okay, we can convert it by using the red weights to map the original data point. For example, is right here, p2, to a new space. Okay, so that is, for example, k1, k2, so on and so forth. K is usually k is less than n, right? Because the weights right here is a neural network. Okay, neural network has several weights, and you have an activation function. You have different layers. You have different neurons. So basically, it maps the original data to a new space. For example, right here, and maybe the p1 is right here. It depends on the weight that you trained. It's based on the activation function you use. So the relationship of p1 and p2 in the original space will be a little different from the relationship in the new space. Maybe the new space can better represent the relationship between p1 and p2. So maybe we use p1 prime, p2 prime. Okay, if there is a cluster in the original space, for example, right p1, something like that. There's another cluster around data point p2. You can expect that those data points will be mapped to the new space, and still those data points will still around p1 and p2, sometimes like this. And maybe I'm gonna draw another point, p3 right here. And of course, we have several data points. Don't forget that we have a lot of dimensions not drawn in this figure, because we can only draw 2 dimensions, 3 dimensions. You have to think about it. We have even more dimensions, okay, in somewhere. That means the same right here. 不要会错意哈。虽然我这边只画2维的资料，因为我们在平面上只画2维，但是你可以想象，就是我们还有第3维、第4维到第 n 维，那右边还有第 k 维，k2、k3、k4 一直到 kk 维，好，那不要会错意的哈。So the best thing is that if we cannot distinguish P1, P2, and P3 in the original space, because there are 2 dimensions, we don't know how to distinguish them. But however, if we do some of space mapping, and P3 can be mapped to some place which is a little bit far away from P1 point, P1 prime and P2 prime, then we can better distinguish the point around P2, P1, P3, and that is a good linear space for us to do such kind of classing or classify. 好，中文再讲一遍哈。有的时候我们在原空间的时候啊，因为资料维度可能很多嘛，资料可能很杂，对不对？然后我们在这上面直接做，比如说 SVM 好了，好，那我们可能 SVM 要切一刀嘛，对不对？啊，或以这3个维度就切3个点就切2刀嘛，好，给它分3片。那有时候你会发现，在某些角度之下，所谓的角度就是我们现在看是 x1 跟 x2嘛，那事实上后面还藏S3一直到 Sn 的这个空间嘛，在某个角度视角之下，因为在那个视角之下，你会有一个projection 嘛，就是那个 projection 就是投影嘛，好，投影的。那在那个投影上，你可能切那个 SVM 的某一刀就切得不好，因为那个投影的角度可能。那如果我们在做这个降维啊，或者是做这个更好的 representation 的时候啊，无论你用 PCA 做，或是用这个 Autoencoder 做，很有可能就是你在降维之后啊，那个资料可以被分得更开啊，可以被分得更开一点。好，这个等一下我跟你讲怎么做哈。那在新的视角上，还有在新的 lens space 里面，或许你做那些 classify 做那些 classing 就更方便，就分得更开。那至于说为什么它可以分得更开呢？好的，这个等一下再讲，好吗？所以有时候lens space 如果你 K 设的好的话，把一些 noise 去掉，所以 noise 去掉，比如说 P3 旁边有很多点啊 ，P33 跟 P3 呢的距离很近，对不对？那如果你 K 设的很不好的话 ，P33 跟 P3 可能在新的 lens space 里面就不小心把那些重要的 information 丢掉，那 P3 跟 P3 可能就合在一起了，就再也分不出来 P3 跟 P33。如果 K 设的不好，如果 K 设的好的话 ，P3 跟 P33 还是会在附近，因为它们可能更紧密了。所谓更紧密的就是说它们靠得更近了，因为 noise 已经拿掉了。那 noise 拿掉之后，靠得更近了。那或许你可以把原本 P1、P2、P3 那3团看起来有点模糊的东西，可以借由 denoising 或是一些设计，让它在新空间里面离得更远。比如说群内的东西离得更近的，群间的东西离得更远，有可能有这种事情发生。所以这就很多时候我们会用 Autoencoder 做一些前处的原因，好吗？好，那我现在开始讲那个 Anomaly Detection。Okay, now we'll talk about why Autoencoder can do Anomaly Detection. Okay, so as I mentioned before, we use the original N data to do such kind of space mapping, right? So such kind of W, which means weight, can perfectly transform the original data to a new space, right? And it can do the same thing, right? And it can do the same thing to recover those data points to the original space by using another weight, which is double prime, right? So how do they do so? We don't know because we do it by training. Those weights are trained, okay? So you think about one thing. If there is a data point right here called P8, originally, these weights can nicely map the original data points P1, P2, P3, and then point around them to a new space, right? However, there's a data point that I have never seen before. And it is far away from the original data set because PA is a little far away. So when we do such kind of space mapping by using weight W, okay, it can map to somewhere, for example, right here. Because those weights, this neural network, this autoencoder network, have never seen such kind of data point before, which is far away from the original data point, P1, P2, P3, and the neighbors around them. So basically, we don't know such kind of mapping makes sense or nonsense. You can think it in this way. These weights, W and W prime, can nicely map the data from here to a new space like here. Maybe I can draw it more time. Because the data point we have ever seen is the red the strange shape right here from left hand side to the right hand side. But if I've never seen a data point in this let's say region, I don't know such kind of a mapping is meaningful or meaningless. We don't know. So if there's a data point PA, which is very far away from your original data point, so the A stands for anomaly. We have never seen it before. So maybe this kind of mapping to the right hand side and recovering to the left hand side does not make sense because the weight is only trained by the point in this strange red region. 好，那我就做这个好，就是我们在做这样的 mapping 的时候，我们 train 那个 W weight 还有 W prime 那个 weight 是拿一些就你已经知道的资料嘛，然后做一个 mapping 嘛。哦，所以左边那个奇怪的范围之内的东西，它可以 map 到右边 map 得很好。那一般来说，你可以画一个类似像等高线的东西哦，就是左边呢，左边那个红色的那个圈圈呢，你可以画一个像等高线的东西往外画。那往外画是什么意思？因为我们说这个空间是一个 mapping 嘛，所以实际上它是一个空间的折叠还有映射啊，就是 projection。那因为我们只看过那个红色区里面的东西啊，所以红色区里面的东西的那些 weight 做这样的转换，我们是很有把握的。你可以画一个等高线在这个红色圈圈的外面，比如说，我换一个颜色好了，比如说桃红色好了啊，所以你可以画一个等高线在这个圈圈的外面啊。一般来说啊。我们应该那因为你知道空间是连续的嘛，因为我们做的这个空间大部分都是因为我们做空间转换只做那个非线性转换嘛，然后我们只做加法跟乘法嘛，对不对？所以按理说这个空间要 map 到另外空间的时候应该是连续的啊。那我再画一个往外的哈，比如说这个淡红色啊，我们再画一个往外的，因为空间是连续的哈，所以这个等高线应该是连续的。可是我们不要讲，我们在做这个 weight 的时候啊。我们只对等高线比较中心的里面那些事情是有把握的，我们根本就不知道这个，因为这个空间很大嘛，我们根本就不知道这个奇怪的 shape， 我们应该是一个高维空间的一个姑且称这个球吧，或者是一个曲面吧，我们根本就不知道外面有什么，我们只知道在中间做得很好，所以当这个 PA 进来的时候啊，我们根本就不知道它那个 mapping 到底是正确还是不正确，因为我们只能根据中间的值往外扩展，啊，外面都是很平滑的，都是很连续的。可是我们根本不知道外面的状况是，就是所谓的 PA， 所谓外面就是那个等高线的外面啊，那这样就很不好，所以我们常常用这个技巧，因为我们的假设是这个中间的东西应该是很准的，然后越往外面，因为资料没看过嘛，所以我就只能假设它的空间曲面是，还有说它的微积分都是平滑连续的，好，就有一个这样等高线的。那我没有看过的资料，按理说它 map 过去，再 map 回来，应该会有个问题。有点像是这个样子，我们讲这个紫色嘛，对不对？当然是紫色的。Okay, so then the shape I write here is that we have a very high confidence that the shape within the red region can be nicely mapped to the right hand side and come back to the left side. But we don't have the data outside this region. Okay, we don't know what is the shape of the outside region. So if there is a data outside of your region, outside of your confidence, it's far away from your original data. You have never seen this data before. Do such type of mapping and recovery might not useful. So that the PA right here, and we go through this weight to the right hand side, and the right hand side data go through back to the weight. It might be right here, not at the original data point. Because our weight does not know how to map the data outside of the red region. Of course, those shapes are there, those parameters are there, those weights are there, but we don't know if those weights are quite fit to the data point outside the red region. Okay, 中文讲这样，就是你那个 PA 呀，因为我们根本就不知道这个外面的 mapping 应该长怎样，或许那边有个谷地，或许那边有个高山。可是我们之前没有看过那个资料，我们不知道那边的形状是个谷地还是高山，所以我们只能用原本的资料，用很平滑的东西去猜 PA 那边的形状是什么。所以非常有可能 PA 那边的形状根本就是一座高山。所以把 PA 丢过去右边，再丢回来的时候，你会发现这个 mapping 不太对呀，它回不来原本的位置。好，所以我们常常用这个技巧来做异常侦测。 也就是说呢，这个东西是我没看过的，所以我的 weight 不知道怎么处理它，我只能很平滑的处理它，好吗？很平滑处理它，表示那边没高山吗？没谷地吗？没什么？不知道啊，没看过，我根本不知道那边是什么，这个很可能没有办法 map 回来 ，OK？ 或是 map 会差很远，好吗？Okay, so that is one of the ways. So if you like to take a look at this code, you can take a look at this one, anomaly detection. Okay, we have several. We have anomaly detection. And please take a look at this one. Okay, it will teach you how to do such kind of detection by using PCA, and of course, all those methods which can apply to PCA lab can be applied on Autoencoder because they have the same goal, right? To do dimension reduction. 好，中文再讲一遍，就是你看到那些 unsupervised learning 的事情，如果他做这个 PCA 的 anomaly detection，实际上你可以用 Autoencoder 做 anomaly detection，因为他们意思在 PCA 跟 Autoencoder 他们意思其实一样嘛，他们只是不同观点做数据的转换，好吗 ？PCA 是纯线性的，然后 Autoencoder 是因为它有它的 neural network 里面有 activation function 嘛，所以它是非线性的转换，好吗？所以这个有些 code 可以参考一下哈。好，那这个就留给你们去看吧。So that is. So I'd like to talk about something about weight. Okay, since we have a neural network, no matter you want to do convolution, dense layers, autoencoder, okay, no matter, you will have a lot of weights, and those weights may cause a problem. For example, I don't know how to design my neural network, so I set a lot of layers, and for each layer, I set a lot of neurons, so I will have a lot of weights to be trained. For example, if I have a neural network and dense data right here, and here's a y. Okay, if I have many weights, I have many weights right here. Okay, sometimes you will figure out most of your weights, they are very close to 0. Maybe sometimes you figure out weight 1 is very close to 0. What does that mean? That means if we the D1 neuron do not need the information from x1 prime to make his decision. So the w1 may be very close to it. Or sometimes, maybe w1 looks like, 1000 x1 prime and minus 2, 1000, 2, Sometimes you figure out, those weights are very large, something like that. But basically, when you do such kind of things, you'll figure out, is that truly necessary to have such large weights? So basically, when we do loss function, for example, MSE, it's like this one, already many times. So sometimes, if those weights are very large, but however, they are extremely large, so I cannot distinguish which one is more important than the other one, because the weight is too high. So sometimes we will have another version of MSE. We will do, we say we minimize this, right? So sometimes we can minimize, That is the original MSE, right? It's the original MSE. Plus, what we have to minimize? We can minimize the entire weight, the sum of the weight, And maybe there is some different versions, like we use absolute value or we use square so that we can guarantee all of them are positive numbers. 好，这么讲哈，我们有的时候会觉得那些weight很怪，就是比如说超大值，减一个超大值，然后再加一个超大值，这没有意义嘛？你把全部都除以相同数目，就用很小值减掉很小值就好了。因为我们刚刚讲过，weight有时候会帮我们判断说这个东西是重要还是不重要。有没有发现那个weight就乱七八糟，有大有小，有超大有超小，真的很多是零。所以有时候我们会希望说那不如大家可不可以再稍微有点综合整理一下，把那些 weight 都尽量压得小一点点好。压小一点点的话，那我们这个MSE 要怎么样修正呢？就变成下面这个样子。除了原本的那一块，就是1/2的那个MSE 之外，我们后面也有可能就是要求他说，你所有 weight 的和的值取绝对值嘛，因为我们刚讲绝对值是指绝对值，因为有可能正很大或负很大嘛，可是它不表示重要的意思，所以我们就先取绝对值，然后把它最小化这个绝对值。那你要知道前面那个 y hat 里面也是有 w 的，对不对？外面的后面的那个也是有 w 的，所以你等一下做微积分的时候其实是没什么问题的 那这个目的呢，因为前面是 minima， 所以我们就是要警惕后面的值除了 loss function 要小之外，额外的，请你尽量的把那些 weight 压在比较小的地方，绝对值比较小的啊，或者是平方壳要比较小的。所以说呢，很多原本大的位置就会变成比较小的。那压的比较低之后呢，因为这个是所有位的一起考虑嘛，因为后面是和嘛，所有位的和，所以我们就会综合考虑一件很莫名其妙的事情，就是那个整个位的和要小，或是平方和要小，那么有很多值啊，就会都降成很靠近零附近。也就是说呢，多做这件事情呢，居然有一个莫名其妙的效果，叫做帮你挑选什么 feature 是重要的，跟什么 feature 是不重要的。这叫做 feature 的 selection。后面那一项，它会尽量让所有的人都下降到和嘛，因为它后面是和或平方和，对不对？好，那自然有一些人呢就会很靠近零的，那有些人值会比较大，它就更符合了我们对整体 weight 的一个观感。整体 weight 里面数字大的就比较重要，不重要的东西因为这个 minima 都会压得很小很小很小，就会几乎靠近，所以几乎靠近零的那些 weight 它所设置的那些 x， 它就会变成说，这个 feature根本就不重要嘛，往后传递的时候它的 weight 一直乘以零，所以 x3的值就一直没有被传递到后面，那就自然的帮我们选择了，原来 x1 到 x6 之间 x3 是里面最不重要的东西，因为它的值它的位很小，它一直没有被传递到后面，所以它不重要。它对后面判断那个 y 那件事情来说不需要它的，那就自然的做到了一个 feature selection 的功能。那这件事情在哪里被描述呢？我也给了你一些那个参考的资料哈。因为它里面有一些数学式子哈，但是我觉得它不适合讲哈。但是所以如果你有需要的话，它就在这里 rigid 跟 Lasso 的 regression 这里有一篇在讨论这两种不同的式子。OK， 好，那我要用英文再讲一遍哦。那这个动作如果用英文上来说的话，它叫做 regulation， 就是这个英文单词，好吗？所以你可以看到下面有一些数学式子的解释，像这个很明显嘛，这个就是一般的 MSE 嘛，对不对？这样看懂吧？好，这个动线一样啊。那如果再加上那个小小的东西呢，就是后面的这一个啊，你注意看到后面那个加是平方和嘛，对不对？平方和，然后它有一个 lambda， 所以我们修正一下啦，就是这里有的时候会有一个 weight 啊，就是 lambda， 它会平衡 MSE 的大小跟右边那个 weight 和的大小，这个我在英文再讲一遍。那这个就叫做 rigid RIDGE。它中文非常的难翻译，它翻译更没有听懂，它叫几回归，能听得懂吗？几就是三级的那个几，它跟画那个等高线有关系啊，但是以后对有机会再说吧哈。那另外一种是没有平方的，是这个版本的，我们看到下面这个，干嘛1.4的那个，它前面不是浪打嘛，浪打只是平衡左边的 MSE 跟右边的那个绝对值的位。好啊，那个浪打这个叫做lasso就是圈一圈的意思哈。对，这个好像没有中文吧？就是回归。那这两种都可以用，所以你有兴趣的话，其实里面的内容该讲的我刚刚都讲过了哈，但是你可以看一下实际上的 code 怎么写，还有他们的指示什么，好吗？好，那我用英文再讲一遍。那So the new loss function which I write here is like this. Okay, the upper one is called the lower one is called okay. They both have a new name, so it's called regulation. The lambda right here is it's a parameter, okay? It's a trade-off between how much weight you like to balance the left-hand side MSE and right-hand side of weight. By using this different loss function, okay, different from MSE, a little bit different from MSE, they can have a lower value of this weight in this neural network. So basically, if we consider those weights of the entire neural network, okay, we can more easily to compare the weight between different neurons and even between different layers. So that if a feature has less weight, that means in this feature is less important than the other one. So that if we do such kind of regulation, we can further have a very nice advantage, which is we can use this weight to automatically select features, so that we also call it feature selection. So we can understand which feature is more important than the other one if we use this kind of loss function. So we can further do feature selection. So we can know, okay, F3, because its weight is less than S2 and it's nearly 0. So the information in F3 is meaningless to find out the target Y. So make sure you, so if you have a very large neural network, okay, make sure you try to apply those kinds of regulation in your code, which may make your neural network more efficient and more reasonable. So the code is right here. So take a look at this code, and they will show you how to apply regulation in your codes. And basically, if you use TensorFlow or PyTorch, okay, they have a specific function to allow you to use grid or lasso regulation more easily. Simply just call a function, which is good enough for you. Okay, so that is